Hello everyone, welcome to this lecture of Control System 2. In this lecture, we are going to discuss the controllability and observability. Okay. We'll see the concept about controllability. So, controllability verifies the usefulness of a state variables. In the controllability test, we can find whether the state variable can be controlled to achieve the desired output or not. The term itself, you might get the idea that the ability to control is what we can call the controllability. Okay, and what we are trying to control here is the state variables. Okay, the state variable. So we'll see the definition by controllability. A system is said to be completely state controllable if it is possible to transfer the system state from an initial state of x of t0 to any desired or final state x of td or x of tf in specified finite time by a control vector u of t, that is the input vector. Okay. So the system is said to be completely controllable when through the any input vector u, all the states can be transferred from the initial state value x of t0 to final state value x of tf in finite specified time. That is what we call by the definition of controllability. And to check whether the system is controllable or not, we have Kalman's test and Gilbert's test. Okay. So first we'll discuss the Gilbert test. So, so Gilbert test of controllability has two cases. One, when we have the distinct eigenvalues. So when consider a state model. Okay, consider a state model like given like this: x dot is equals to ax plus bu, and output equation is y is equals to cx plus du. Okay, with the transformation variable z, okay, we are modeling or we are transforming this x state variable to z state variable using this relationship as x is equals to m into z, where m is called as the model matrix and z is the transformed state variable. So x dot is equals to x plus bu, that is the original state space model, will now be transformed to the new state space model with the state variable as z. So the state equation will become z dot is equals to capital lambda z plus b bar u, and output equation will be modified as y is equals to c bar z plus du. Okay. Now this delta or the capital lambda will be defined as m inverse into a into m. Okay. In many we call it as the Jordan matrix as well. Then matrix B bar is given by the definition m inverse into B. C bar is equals to C into M, and the D is as it is. Keep those things in mind. In this case, the necessary and sufficient condition for the complete controllability for the given system is that the matrix B bar must have no rows with all zeros. This matrix B bar should not contain any row with all the zeros. This, how do we get the value for the B bar matrix? M inverse into B. If any row of the matrix B bar is 0, then the corresponding state variable is uncontrollable. Okay. So according to Gilbert's test of controllability, when the system is having the distinct eigenvalues, the system is said to be completely controllable when the B bar matrix should not have 0 element or 0 row. Okay. Then and then only the system is said to be controllable. Otherwise, the system will not be controllable. It will be uncontrollable. Okay. Another case when the system has the repeated eigenvalues, we'll see the system matrix cannot be diagonalized in this case. Correct. In the case of the model matrix, using the model matrix with this relationship, we get this diagonal matrix. Correct. We get this diagonal matrix or the Jordan matrix. But when the system will having the repeated eigenvalues, in this case, the system matrix cannot be diagonalized, but can be transferred to the Jordan canonical form. So consider the original system as the x dot is equals to x plus du and y is equals to cx plus du. Now the state model can be transferred to the Jordan canonical form with the transformation using x is equals to m into z, where m is the model matrix and z is the transform state variable vector. Okay, the transform state model will be given by z dot is equals to j into z plus b bar into u and y is equals to c bar into z plus du. Okay. The j will be given by m inverse into a into m. Is the same definition, but the thing is, it is not for the distinct eigenvalues. This is the Jordan canonical form. Okay. So that's why in this matrix, the capital lambda, this delta here, is also called as the Jordan matrix with this definition, provided for the repeated eigenvalues. So J is given by J is equals to M inverse into A into M. B nu or B bar is equals to M inverse into B. C bar is equal to C into M, and the D is as it is. For this case also, okay, the system is said to be completely controllable if the elements of any row of the B bar that corresponds to the last row of each Jordan block are not zero, and the rows corresponding to each state variables must not have all zeros. Okay, so the matrix B bar should not have all zeros. Okay, the rows of matrix B bar should not have all zeros. So this is for the Gilbert's test for the controllability. Now we will see one example for it. Consider matrix A, the system matrix given as this, and the matrix B is given as this. Okay. Matrix A contains the element 1, 0, 2, 0, 2, 1, 0, 0, 3, and the matrix B is 1, minus 1, 1. Now to use Gilbert's test, what we need to have, we need to first calculate the model matrix. How do we get the model matrix? Using the eigenvalues. Okay. So let's first calculate the eigenvalues. The eigenvalues here are calculated as 1, 2, and 3 are represented by the lambda 1 equals to 1, lambda 2 equals to 2, lambda 3 equals to 3. Now consider the characteristics equation using the lambda or the eigenvalue a minus lambda I or lambda I minus a, the modulus of a is equals to lambda minus 1, 0, minus 2, 0, lambda minus 2, minus 1, 0, 0, lambda minus 3, or this one also. Okay. It can be shown that the eigenvector can be obtained as any non-zero column of adjoint of a minus lambda I. Okay. This should be lambda here. Thus, okay, adjoint of this modulus a minus lambda I is equals to, given by this matrix, 2 minus lambda into 3 minus lambda. Here you can see for the first it is 2 minus lambda into 3 minus lambda minus 0 into negative 0, then plus of minus of 2 to plus lambda. Okay, so this will be minus 2 in bracket 2 minus lambda. So similarly for the other positions, Let us find the eigenvectors corresponding to every eigenvalue for lambda1, for lambda2, and for lambda. That will be obtained when we put this into this adjoint. Put lambda1 there, you will get the first column as 200, or you can consider the 100 as well. Similarly, using the lambda2 and lambda3, we get m2, that is the eigenvector for the lambda2, eigenvector for the lambda3 is 111. From this, we can formulate the model matrix M. This it is 100010111, as in the that makes the three eigenvectors for corresponding eigenvalues. Okay. From this model vector, a model matrix, we'll calculate the M inverse. Okay. From this M inverse, we'll calculate the B bar or the B new given by the equation M inverse into B. That is given by M inverse into B, and we'll calculate and find the value. Now the B bar is equals to is calculated, and it is obtained as three elements 0, -2, and 1. Okay. So here you can see the first element of B bar is 0. That makes the system as uncontrollable. That makes the system uncontrollable. Okay. So this is it for the today's lecture. We'll continue in the next lecture with another example and the concept of observability. Thank you.